3 in front of the first one, and a 3 under here. Why are you going to do that instead of the other way? It's 3 over 3 is 1, right? 3 over 3 is 1. So that makes this nice. So this leaves me 3x minus 7, and then x plus 1. That is the factored version of that. So I can come back over here and write this as 3x minus 7, and then x plus 1 equals 0. And now that it's factored, I can set each factor equal to 0. So I set 3x minus 7 to 0. I set x plus 1 equal to 0. Let's do this one first. Just move the 1 over. Negative 1. On this one, I have to add 7 to both sides first, and then divide both sides by 3. 7 over 3, which is about 2.33 repeated. Okay, any questions there? I mean, if you're not happy with this, I'm about to use a quadratic formula as well to do it. That would be our second option if you didn't want to do this. So if I want to do the quadratic formula instead, then I would have to do, well, I'm trying to solve this, right? God, I keep on putting square minus 4x minus 7 equals 0. So I have to use that formula, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. I've got to use that formula, right? Where here for us, a is 3, b is negative 4, and c is negative 7. And just plug everything in, and we should, at the end of this, we should get these two answers. Let's see. So x equals, let's see, negative b is the opposite of what we have for b. So we have negative 4. So negative 4 should give me positive 4, plus or minus the square root. B squared means I'm going to square negative 4, which gives me positive 16. Minus 4 times a was 3, times c, which was negative 7. All of this over 2 times a was 3. And I told you all to look at this and count how many negative signs you see, right? You see 2 of them, which means it's going to become a plus. So I'm going to go 16, 4 plus or minus square root. I'm going to go 16 plus. Then just take these 3 numbers and multiply them together. So what is that? 12 times 7, 84? It's 84, I believe. So I'm adding 84 to this. All over 2 times 3 is 6. Hey, isn't that 100 underneath there? 16 and 84? What's the square root of 100? 10. So this would become 4 plus or minus 10. So I realize that that's 100. Square root of 100 is 10, so no more square root, over 6. And now I have 2 answers. I have to take the plus and the minus. So if I do plus, I'm going to do this in my head. 4 plus 10 is 14 over 6. That reduces to 7/3. 2 goes into both. 4 minus 10 is negative 6 over 6, and that's negative 1. Same 2 answers. Y'all see that? I don't care which way you do it. So step 1 done. Step 2, vertical asymptotes. Now we set the denominator equal to 0. And fortunately for us here, right, we do not have to do this because this has a GCF. I can pull an x out of both. Set each one equal to 0. I get 2 solutions, 0 and 9. That sucks. I'm going to have 5 test points, right? I already know that. Got 2 verticals and 2 x-intercepts. I'm going to have 5 test points. Any questions? Y'all seem like eerily quiet right now. Does this seem like there's a lot of shit to have to keep track of? Yes? So don't lose sight of a conversation I had with you earlier in this semester about, why we're here, what we're doing here. Like, you would never, ever need to graph a rational function in the real world, ever. Like, never, okay? This is about, can you keep all of this stuff, if you're given some sort of procedure. I mean, the math part is complicated, it can get complicated, but other than that, the bigger picture is, can you follow a procedure without making mistakes and be meticulous? And that's what it's about, all right? All right, third step, horizontal asymptotes. Okay, I'm going to compare the degree of the numerator and denominator. And check it out. For the first time, they're both equal, aren't they? They're the same. And this, I believe, is case C. Right? Is that what you have on your notes? This is case C. This is the one that everyone gets tripped up on. I don't know why. I mean, I guess I do know why, but whenever they're the same, okay, whenever they're the same, you're going to have a horizontal asymptote. It's going to be a horizontal line, and here's the equation of the horizontal line. It's going to be y equals, remember, y equals, if I give you y equals a number, you have to remember from when we were studying lines that that's a horizontal line, okay? Y equals a number. But the number, what it actually is going to be the leading coefficient of the numerator, this number, 3, divided by the leading coefficient of the denominator, which is a 1. 3 over 1. And of course, 3 over 1 is 3. So if these two are the same, you then have to go look at the numbers in front. So if this would have been like a 3 and this would have been a 6, then it would have been 3 over 6, or 1/2. If this would have been, I don't know, a -3 and this would have been a +2, it would have been -3/2, or 1 -3 over 2. Okay, so case C, I think, is the one where, I guess, because it's so different than the other cases, right? The other two cases are straightforward. All right, let's draw a picture. God, this is going to suck. Okay, x-intercepts. We have one at -1. -1. Put it right here. I have another one at 7/3, which is 2.33. I'm going to have to kind of eyeball this. If this is 1, and this is 2, and this is 3, 2.3, I'm going to just approximate it here. This is 2.33. Okay, there's my other x-intercept. I just realized my graph is going to go off camera because I got to go all the way out to 9 for vertical. So I'm going to redo this. I need to give myself a little more room to get it all on here. Okay. So -1. There's an x-intercept. 1, 2, here's 3. So right around here, 2.33, I have an x-intercept. Okay, verticals. I have 2 of them, at 0 and at 9. So at 0, and way out here at 9. And then I have a horizontal asymptote at y equals 3. So here's the way you do this. For your horizontal at y equals 3, y equals 3 means you go on the y-axis, you go up 3. So let's say 1, if that's 1, let's say that's 2, let's say that's 3. Okay, that's my horizontal asymptote. But you only draw it at the edges. So I'm going to come out here to this edge, and then over here at this edge. You see? Don't draw it all the way across. If you draw it all the way across, you're going to think you can't go through it, and it's going to mess your picture up. I promise it's going to. All right? Questions on the setup? Nice. What's next? Test points. Okay, I'm going to have 5 of them. So I need something over here. -2. Hey, negative 0.5 again, right? Between this x and this vertical. Negative 0.5. Oops, 0.5. Let's see. Something between here and here. What do you want? 1? All right, something between here and here. Wow, you have a lot of choices here. 6? One more. 10. There they are. 1, 2, 3, 4, 5. You're just making sure you have one in between each x-intercept and vertical, right? And then at the ends. So you have the 2 at the end, and then here's an x-intercept and a vertical. I have 1 between there. Here's a vertical and an x-intercept. I have 1 between there. Here's an x-intercept and a vertical. I have 1 between there. And now you have the pleasure of plugging those numbers into that nasty, ugly thing, right? This is just the tedious part. Make sure you're taking your time, using your calculator if you need to. We need -2 in there. We need -0.5. We need 1. We need 6 and 9. Or sorry, and 10, sorry. So this part right here is probably going to take you a good, 5 minutes to 10 minutes. I mean, to get it and to make sure you're being careful with things, right? I'll just do the first one, okay? So I've got to do 3 -2 squared minus 4 times -2 minus 7 over -2 squared minus 9 times -2. Order of operations. Be careful here. Anytime you square a negative, it becomes positive. So this should give me 3 times 4, that's 12. 2 negatives multiply to be positive, so plus 8 minus 7 over 4. 2 negatives multiply to be positive, so plus 18. I believe I get a positive number on top, right? That's 20 minus 7, 13. And on the bottom, that's a positive number, 22. Again, all I care about is that it's positive. Questions? You got to do that for the rest of them. I'm not going to. I'm just going to tell you what they are. This one does also switch. It's negative, positive, negative, positive. I could show you how to figure out whether or not it switches or not, but the time it would take to explain that is more than you just plugging them in. Like, it's not worth me going through it. Okay, so I'm going to plot the points. Is that all right? And then we're going to draw it. So at -2, we're positive, up here somewhere. At -0.5, we're negative, down here somewhere. I'll just erase that. At 1, we are positive. At 6, we're negative. And at 10, we're positive. Take 30 seconds to try and draw it yourself. You've got the points plotted. See if you can draw it. clock is loud. You hear it? All right, here we go. From this point, I've got to get up to the magnet. Here, connect, connect, and then as I draw this way, the vertical barrier forces me down. Over here, to the left, I've got to go up, can't come down, right? Vertical barrier. Connect, connect, and when I go this way, I've got to go down. So I'm going to just connect this all together like this, drop it down. This one is a little tricky. To the left, I've got to go up, okay? Can't come down. And as I go to the right, I've got to flatten out towards that. So it's going to look something like that. Do you all see why I'm telling you when you draw the horizontal to not draw it all the way through? Do you all see why? Because if you do, right, and you're trying to do this, you're going to be like, oh, wait, and it's going to confuse you. You're going to be like, I can't cross it. No, the horizontal only tells you about end behavior. It does not tell you about what happens in the middle. It's always frustrated me because most of the tutors in the tutoring lab draw it all the way across, and it just drives me crazy because it doesn't go all the way across, just the ends. Not their fault, it's probably the way they were taught. So, okay, so I've done what, 3 rational functions now? And we've seen every case. We've seen the case A, B, and C. We've seen all of them. So we're going to move on. I have about 25 minutes. The good news is that technically we are done with rational functions. All right, in terms of sketching them, there's no more. We can put them behind us. So here's where we are. So far in this class, all right, so far, we have done linear functions. In other words, if we had a function f of x equals mx plus b, y equals mx plus b, this is a line. Everyone here should be able to graph a line. We started, earlier in the class, we learned how to graph lines, so we should be good here. We now know how to do quadratic functions. Those are functions that look like this. Ax squared plus bx plus c. We know how to do that. There was a whole set of steps. Does it open up? Does it open down, right? What's the vertex? Oh, do a quick sketch. Okay, find the x-intercepts. Find the y-intercept. Draw your picture. You've already had a test on that. And then we did polynomials. Okay, these, I'll give you a specific example. This is something like crazy, like x to the 4th minus 3x cubed plus 2x squared plus 6x. That's like an example of a polynomial. And this is the one, we had a set of steps for this, right? It was like, first do the leading coefficient test, figure out what the end behavior is, use that table. The one I got wrong in class, remember that? Okay, so we did that. Then we found the x-intercepts. That was the hard part. And then that bounce cross thing, right? So we know how to do those now. And now we just studied rational functions. And that's any function that is a polynomial divided by another polynomial. And we have the whole set of steps for that. X-intercept, verticals, horizontal, case A, B, or C, draw a picture, test points, use all the information, draw your picture, right? So that's what we've done. 2 more, and we're done with all the functions we study in college algebra. Okay, but this one's the hardest. This one I think is the hardest one. Okay, rational is the hardest. So the next one is exponential. And you'll see that when it comes to exponential, I think these are going to be the easiest for you to draw because we're just going to use our calculators. Okay, so the question is, what is an exponential function, all right? And I hope I've tried to illustrate in this class a little bit about how each of these functions play into the real world a little bit. You know, lines, you know, you work hourly. I think we talked about quadratics, parabolas, satellites, things like that. polynomials, stock market, I think we talked about, anything that fluctuates up and down, rational functions. I was talking about winning the lottery, living to a certain age, the life of a light bulb. Those rational functions are good for modeling those. Exponential, they are their own animal, right? But they model something else in the real world. So that's where I want to start. I want to start with a real world example. So let's do this one first. I'm going to give you, so we're talking about exponential functions right now. I want to give you the bacteria example. All right, so do y'all know what a Petri dish is? Have any of y'all taken biology? So a Petri dish is a little plastic dish that is, what's the word I'm looking for? Sterile, right? It's a sterile dish, meaning they have like a little jelly on the bottom of it, and inside of it is nothing. Nothing living is in it, okay? It's sterile. And so what you can do is you can go and take a cotton swab and maybe go swab the door handle over there and just rub it onto the Petri dish and close it, and then come back a week later and see what happens. And most likely you're going to get bacteria off that door handle, and it's going to start duplicating inside the Petri dish. And you're like, oh my gosh, that's nasty, right? So the way bacteria work is that you start with one bacteria, just a single bacteria, and then after a certain amount of time, it will split into two, or sometimes it splits into three, depending on the bacteria. And it also depends, like that amount of time is different for every bacteria. Some bacteria duplicate every 2 hours. Some, it takes a day. It just depends. So I'm going to give a hypothetical situation here. Let's say we have a bacteria. This particular bacteria, I don't know what it is. I'm making it up, okay? This bacteria triples every day, okay? Find a function which models its growth. Okay, so let's start this with a picture. Do you understand the idea that you have a bacteria and a day later there's going to be 3 of them, right? It's going to split into 3. So I'm going to do this with this picture here. We start out with this one bacteria. There it is, right? And this is going to be day 0. Okay, so I put the bacteria in the dish. There it is. It's just one of them. Now, day 1, we're going to have how many bacteria? 3, right? So this thing is going to split into 3 bacteria. I don't think bacteria have emotions, but we'll just say that they're happy. Okay, day 2, what happens? Triples. How many are we going to have? How many are we going to have? How many are we going to have?
6.
You sure? Each one triples. 9, right? Each one of them triples. Right? So you got 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Now you have 9, right? On the second day. What about day 3? How many are you going to have? 27. Because each one of those triples. Right? Each of the 9 becomes 3 more. It's starting to get crowded in here, right? I don't want to draw these. You get the idea? So let me draw a table. Let me draw something other than me drawing bacteria. Let's do it this way. Let's make a table like this. Let's say this is days, whatever, and this is bacteria. On day 0, we had 1. On day 1, we had 3. On day 2, we had 9. And on day 3, we have 27. Right? How many are we going to have on day 4? 81. How are you doing that? You're just tripling this, right? You're taking, like, you take that, multiply by 3, you get 3. Take that, multiply by 3, you get this. Take that, multiply by 3, you get this. Take that, you multiply by 3, you get this, right? Understand? So how many on day 5? So we might need a calculator at some point, right? May as well get it out because you're going to need it, all right, for the rest of today. So what's 3 times 81? What is it? 243. Okay. Could you tell me how many on day 6? Sure, just multiply by 3, right? But let me ask you this. How many are going to be there on day 32? So imagine that table continued. How many are going to be there on day 32? See, here's the problem with what's going on. Right now, in order for us to figure out the next one, we have to, right, if I want to know what happens on 6, I have to triple that, right? If I want to know what happened on 10, I would have to do 6, 7, 8, 9, then 10, right? Then I could tell you what happens on 10. Am I making sense? Like, if I want 32, I've got to go all the way from here to 32 to get to it because I'm tripling it each time. Understand? Is there something better that all we would have to do is give this number and it would spit out this? This number and it spits out this. Forget the tripling. I mean, it's important to understand that that's what's happening. But is there some function, right? That's what this is asking. Is there some function out there that what I do is I plug in this number and it spits out that number? So I plug in 4, it spits out 81. Plug in 5, it spits out 243. Is there one? What do you think? I mean, we're studying it, there probably is. But here's the thing. It's not a linear function, okay? It's not quadratic, it's not a polynomial, and it's not a rational function. None of those will work. None of them do. There's only one type of function that's going to model this behavior. So here's the way I'm going to get you to see it. Do you agree that 3 is the same as 3 to the first power? And that 9 is 3 squared? And that 27 is 3 cubed? Yes? And 81 is 3 times 3 times 3 times 3. That's 3 to the 4th power. And 243 is 3 to the 5th power. So do you all see the connection? Right? What about that first one? Following this pattern backwards, this would have to be 3 to what power? 0, is it? Any number to the 0 is 1. Any number to the 0 is 1 except 0. I should take that back. 0 to the 0 we don't study in here. This is undefined. Okay? You do that in calculus, not here. Any number other than 0 raised to the 0 is 1. Which means that the function, what stays the same in all of these? The 3, the only thing that changes is the power. So my function should be, you give me the input, right? And I will take 3 and I will raise it to that input. 3 raised to the x. Go back and think about lines, quadratics, polynomials, and rational functions. On all of those functions, our variable x lived down on the bottom, not on the top, right? It was always like x squared or x cubed or x to the 4th. We never had the x up in the what we call the exponent. The x was always on the bottom, which we call the base. Here, the variable's up here, and the base is a number. It's switched, right? Don't confuse this with x cubed. These are not the same thing, right? So this looks like this would work. It looks like this is it. So here, if I want to know after 32 days how many bacteria are there, I would have to take 3 and raise it to the 32 power. Yikes, I'm going to need my calculator for that. So on your calculators, you should have a key to do this. On this particular calculator, which is the TI-30X, the one you're supposed to have for the class, but you're going to have to type in 3, and then there's this caret key, and then 32. 3, the caret key is on the left side. Everyone's got different calculators. I'm glad you got one, yes. You find your key? Everyone's got kind of different keys, so make sure you can do this. I'm going to do this and see what happens. Oh my gosh. this is what my calculator says. I'm going to not have enough room here. It says 1.853020189, and then it says times 10 down there, and then it says 15. That's what my calculator says. Yours might say something like EE15. What is yours? Yeah, same thing. Anyone got something different than this? So what does this mean? What does this 1015 thing mean here? Because 3 to the 32 is not 1.8, right? Can't be. 3 times 3 times 3, 32 times, cannot be 1.8. This 10 to the 15 means you need to move this decimal point 15 places to the right. Okay, so this is what's called scientific notation. We actually skipped that in the beginning of the class. So you need to realize that you take this decimal and you move it 15 places to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Right there. Fill these with zeros. So this is 1.853020189123456. That's how many bacteria you have. Let's see, what is it? Is this even a number we know? Let's see. Okay, this is ones, tens, hundreds, thousands, 10,000, 100,000, million, 10 million, 100 million, billion, 10 million, 100 billion, trillion. After gazillion. It's huge, right? This is a huge number. That's how many bacteria are there after just 32 days. How did we go from like one bacteria, 3, 9, 27, these are pretty small numbers, right? And get to that so quickly, right? This grew extremely fast. Extremely fast. That sort of growth is what we call exponential growth. And you hear this all the time on the news. Just watch TV, watch the news. They always throw that word exponential out there. What they mean is it's growing very rapidly. Okay? So this is our first kind of example of exponential, an exponential function, 3 to the x. Now, while I've got us thinking about these very large numbers, I want us to talk about something that might be relevant to you. Do y'all know what's happening right now with the college basketball March Madness? Show of hands, y'all know what's going on? March Madness? Really? It's only 2 people, really? Everyone else not